Chapter 13.
Amazing.
In Santana, if you have when you get your computer, you can kind of follow along with these have the same pictures and stuff that's in your online textbook. So I'm just showing you some of the stuff that's in the textbook, and you can kind of read along, take notes, and that sort of thing. He's filming the class, and I put them all on YouTube. So if you ever miss for football or whatever, you can watch it on your phone or watch it later, that sort of thing. Okay, so the telescope was invented, not invented, but perfected by that guy. 10 points if you can tell me what that guy's name is. He perfected the first telescope, and we already learned this. That's why I'm asking you.
Galileo.
And by the way, Santana, what I do is I divide the class up into teams, and each team is a different color. So this is the pink team, this is the orange team,
We were doing that.
and I keep like a running total. And like whatever team finishes in first,
I don't know, I was just
4 bonus
kidding.
points on the test. Second place, 3 bonus points. Third place, 2 bonus points. So that's what we're doing now. So why don't you for now be on Aubrey's team because she requested. Green is correct. Green is incorrect. Pink is correct. Orange is correct.
Or should you want to go for it?
Purple is correct. Anyone else? This guy is his name is Galileo. Galileo was the one that perfected the telescope, and he's showing it to some king or something there. Is that a pope? What is that? Does it say in the reading?
Dodge of Venice.
That's that school.
I don't know what that is.
School.
This is this type of telescope. The kind you see that are long and thin are called refracting telescopes. This is one right here. This is a refracting telescope. And refracting scopes, this one's a little bit broken here. Somebody knocked this over one time, I remember, and messed it up. But anyway, a refracting scope takes light. Light goes in through the lens, and it focuses the lens, just like glasses do. It changes the angle that the light is coming in and focuses it. And there's another lens, your eyepiece, and the combination of those two lenses magnifies the object. It's the same way a microscope works. You can make the object bigger, and the longer the scope and the wider the lenses, the more magnified the object will be. Yeah.
How far out can you see with that one?
Well, you can see with the naked eye. You can see a star that's 40 light years away, but it makes things about up to maybe about 80, 100 times bigger. Mm-hmm. However, if you make a far-off star 100 times bigger, it's still going to look like a far-off star. They're so far away, they're just points of light. Mm-hmm. So telescopes aren't really good at looking at stars that are real far away because they're just tiny points of light, even though they're real bright, so you can see them from far away, but they aren't going to get any bigger with a normal telescope. But this will you can see, with a scope like this, you can see planets. Really, you can see them bigger than they actually are. The moon, it's great for looking at the moon. If you put a filter over it, you can look at the sun. And we're going to use a telescope to look at the sun. So there's lots of things telescopes can do. Chris, you missed a quiz, so you're going to have to make that up. Refracting telescopes, though, have some problems associated with them. The lenses are hard to make. The lenses are glass. They're real heavy. A glass lens is heavy. The light has to pass through it. If you're going to make a big glass lens, it's got to be a big piece of glass. You have to polish 2 sides correctly, and they're cumbersome. And the focal lengths are usually long for a big glass lens. So you have to have a long scope, and that's sometimes hard to deal with. So refracting telescopes, by the way, refract means to bend. So a lens bends the light. Refracting telescopes are good for a small scope, but once you start getting a big scope, there's a lot of problems associated with them. Another problem with a refracting scope is something called chromatic aberration. Can you say chromatic aberration?
Chromatic aberration.
That's when, if you're looking through a scope, you can see a little bit of a rainbow. And I'll let you look through this. A little bit of a rainbow around the edges of things. So I have this scope right now focused outside. Oh, here we go. So I want y'all to come look at this. And be careful because the desk is slidey, okay? But I want y'all to look through this, and I want y'all to notice that the edges of things, like I got it focused on the edges of some of the trees out there. The edges of things, you can see a little rainbow. It's called chromatic aberration. So everybody come up here and look. Now there's two lenses. There's a top viewer and a bottom viewer. Look through the bottom viewer and be careful with it. You might want to hold it so it doesn't fall. But notice that the edges, can you see a little rainbow around the edges of things?
Yeah.
Do you see that, Charlie? Yeah. Everybody take a look through that scope.
Oh, wow. It's pretty cool.
Yeah, honesty is alright.
This climb. I probably can't sit there.
Are we looking at the bottom?
Yeah. Well, that's a game changer. Bless you.
Thanks.
Thank you.
Chris also got put to watching or filming.
Am I supposed to be looking at?
Hold on, what? Oh, yeah.
Oh wow. It's really cool.
Fascinating.
What kind of device is that?
You want to take back over?
What kind of device is that? Oh yeah.
That's my bike.
That's
No,
the big
same
one over there.
This is a bigger one.
It's real big.
Also done it.
So did you notice the edges of things kind of had a rainbow-like look to them? So we call that chromatic aberration. And it's because when light hits a lens, the lens breaks the light up a little bit into the separate colors. Blue is refracted a lot more than red. And so when light goes through a lens, it tends to spread out a little bit, and you get this chromatic aberration. That's a problem with refracting telescopes. And so for all these reasons, scientists like to use reflecting telescopes more. This one right here is a reflecting telescope. And the way it works is, it's got a mirror on the inside. You take the end off here. Light goes in through the hole here. This is just an empty hole. And in the back of the scope is a mirror. And I don't know if y'all can see that mirror from where you are. Can you see a mirror in there?
Yep.
Can you see? Santana, can you see that mirror? Mirror there? Can y'all see? Can you see it on film?
Yeah.
Really? Mirror. Can you see the mirror? There's a mirror in there. There's a mirror. A mirror makes a reflecting telescope. The light goes in, it hits the mirror. The mirror is slightly bent, it's concave, so it focuses the light to another mirror that sits in the middle of the scope. It actually sits right here. There's a mirror right here behind this little thing. And that mirror shoots the light up through this hole, and you look through this hole at the image. I can see Sam's shirt right there, blue striped shirt. That's where it's looking at right now. This is a reflecting telescope. Reflecting telescopes don't have chromatic aberration. They don't have that problem that one had with seeing a rainbow of colors. The light reflects completely, and all the light stays together. Another thing about making a mirror in the back of the scope, the mirror can be very light. It doesn't have to be real thick and wide like a lens. It can be just a thin layer of silver that's painted onto a plastic surface. And if you shape the plastic right, you can paint a thin silver layer that reflects the light. So you can make it really light. And so most observatory type telescopes, like these big ones, that's on the top of a mountain in Hawaii, those big scopes, they're called observatory telescopes. They have these huge mirrors that take the light in and reflect it and collect a whole bunch of light and reflect it, and you can see images. And those scopes are so big that they have to have covers. And this whole thing right here is a cover that can be pulled back and opened up so that you can see the sky, and then closed up to protect the scope from harmful weather and that type of thing. So we call that an observatory. An observatory is a telescope with a roof over it, and the roof can be open and closed. And the telescope's so big that you can't really move it around like these scopes can. This is a 4.5-inch telescope, meaning that's the diameter here of the mirror. The mirror is 4.5 inches wide. That telescope right there, I think, is a 20-meter telescope. So the mirror is 20 meters wide. Y'all know that's like in football, that'd be like a quarter of the football field. That's a big mirror, way bigger than this. The bigger the mirror, the more light it collects, the more it can focus, and you can see objects better. You want to see video footage of telescopes?
Why are observatories so expensive? Is it really hard to build that big of a mirror?
Yeah, they have to have a lot of computers associated with them. They're usually at the tops of mountains. You got to get all the hardware up there.
Right.
I mean, think if that's a 20-meter scope, then this building is about half a football field inside. It's a big building.
Right.
So, yeah, there's a lot going on with big observatories.
The following KQED production was produced in high definition.
How do we make this full screen?
Well, people sometimes ask me, how did you get involved in astronomy? I said, I got born. What's your problem?
Meet John Dobson. He spent most of his 92 years on this planet contemplating the cosmos, simply because it's there. You might call him the quintessential amateur.
The word amateur comes from the Latin word for love. And an amateur astronomer is someone who goes out and could be just idly learning constellations or looking through a small telescope, or it could be going all the way to doing valuable scientific research with all of it.
In 1968, Dobson co-founded the San Francisco Sidewalk Astronomers Club, sparking an international renaissance in amateur astronomy.
And our meeting was just meeting on the sidewalk with our telescopes. So we became famous all over the city. All over the Bay Area, people knew. If you want to look through a telescope, go to Jackson and Broadway Street on any clear night.
These informal gatherings now happen on sidewalks and hillsides the world over.
We have a star party like this 4 times a year at a solstice or an equinox, and this is near the winter solstice. And the telescopes are provided by the San Francisco amateur astronomers. You can get started for less than $200 with something that will be worth looking through. It'll show you things you won't see otherwise.
With just a small telescope, you can see the rings of Saturn, the craters of the moon, the atmospheric bands and moons of Jupiter, star clusters, nebulae, and galaxies millions of light years away. With larger telescopes, the volume of space that you can see goes up considerably. You can go up to where you see thousands or hundreds of thousands of galaxies. You can see stars exploding a billion light years away. There's no limit to what you can see out there. Is one of the appealing things about the universe.
Since the dawn of consciousness, humans have been gazing at the stars. But what we could see was constrained by the limitations of the human eye. That changed in 1609 when Italian scientist Galileo first constructed a simple refractor telescope to enhance our ability to investigate the night sky.
This type of telescope that you're seeing here is a refractor telescope. And it's what, everyone kind of thinks of when they think of a telescope, they think of a refractor.
A refractor telescope receives light that's transmitted from objects in space and bends or refracts it through clear optical lenses into an eyepiece. It's a simple, durable design that produces sharp, steady images. But because glass lenses must be carefully crafted and treated in order to transmit color accurately, larger models tend to be significantly more expensive than their smaller counterparts. A reflector telescope uses mirrors to bounce or reflect light into an eyepiece. Although less stable than glass lenses, mirrors are cheaper to manufacture, and they reflect all visible wavelengths evenly, producing a bright, color-accurate image for a reasonable price. And with both types, size matters. A telescope's total power depends on its aperture, the diameter of its primary lens or mirror. That's where John Dobson comes in.
Up until John Dobson.
Okay, I'm going to stop that there. There's more to it, but I just wanted to. That shows you pretty well how those scopes work. So there's different techniques we can use to get better pictures. And where's my mouse? I lost. Oh, here it is. Found it. Okay, so what can you do if you want a better picture of the sky? If you want a better picture of Jupiter, you can use. First of all, you can make your telescope bigger. Larger scopes can see close up better. But of course, it's more expensive. These large. This picture right here is called the VLT. You know what VLT stands for?
Very large telescope.
Very large telescope. That's really what it's called. This is the Very Large Telescope. It's in Chile, in South America. It's on the top of a mountain, and there's actually 4 scopes, and they can all look together at the same thing. And if they're all looking at the same thing at the same time, it's like the 4 scopes are combined into one big scope. And they can see things even better than the Hubble Space Telescope can. They're very big. Each one of them has I think a 10 or 20 meter mirror. I mean, they're huge. So anyway, you can make your telescopes bigger. You can make the exposure time longer. So if you're looking at something just with the naked eye, you just see it as it is. But what you can do with computers is you can let the light hit the computer, and the computer can store that light over a long period of time. You take what's called a long exposure. Anyone here ever taken a photography class? And do y'all know you know you can take a longer exposure and get more light and get a better picture of something. If you lengthen the exposure time, you can get a good picture. And you can see something that's real dim. If you take it for a long exposure time, it becomes real bright. Active optics. Active optics is the idea that you can change the shape of a lens. You can change the temperature. You can keep the temperature of the scope constant. There are tiny movements of air inside one of these large observatory scopes, and if you keep the air really still in there, if you slightly adjust the mirror, if you change the focus barely to account for shifting temperatures and air currents, you can get a better picture. We call this active optics, making small changes in your scope to get better pictures. And then there's something that's related called adaptive optics. You can see this laser that's being fired out of this telescope. What observatories will do is shoot a laser up into the atmosphere. Did you know that the atmosphere moves a bit? Have you ever seen stars twinkling? The twinkling of a star is because of the atmosphere moving. You can see the atmosphere moving real well when it's really hot. Have you ever looked at down a road, you're driving on a road and it's real hot and the heat's coming up off the road and you can kind of see it shimmering? Y'all know what I'm talking about? The atmosphere does that. The atmosphere shimmers a bit. And what it'll do is it'll take a star or a planet or something you're looking at and it'll shake that star or planet. And it makes it so that the image is blurred. So whenever you're looking through the atmosphere at a planet or something like that, it's blurred because it's shaking. What these observatory scopes can do is they can shoot a laser into the atmosphere, and the computer watches the laser beam and watches how the laser beam shakes. And the computer figures if the laser beam is shaking like this, then the object you're looking at is going to be shaking like that. And the computers now are so sophisticated, this is incredible to me, that the computer can say, okay, if the laser beam shifted right a little bit, that means the planet must have shifted right a little bit, and I will shift my viewing right a little bit to account and make it so that star or planet actually doesn't move in the brain of the computer. And the computer, using this laser beam, can get rid of all the shaking. Even though it's vibrating back and forth maybe 1,000 times a second, the atmosphere will move back and forth that quickly, shaking the thing. The computer can cancel that out and get it to be still. It's amazing what they can do. We call that adaptive optics. Can you say adaptive optics?
Adaptive.
Y'all didn't say it that enthusiastically. Question? Hold on, let me cut this off while you're asking your question.
The Large Binocular Telescope is one of the world's most technologically advanced.
Okay, go ahead.
Can just any regular person go to that telescope?
No. You have to be a scientist and have credentials and stuff. Now they do. I think they do tours of some of these observatory scopes where they'll take you around and give you a tour and show you some of the inside, but you won't be able to look in the scope and work it. We get our pictures from these scopes. All the pictures that you'll see in this book and most astronomy books are from these big observatory type telescopes. And it makes it so when you look through your own scope, you're like, that's kind of lame. If I show you Jupiter through this scope, you'll look at it and it'll be this little tiny circle, and you might be able to see the stripes. If you got good eyes, you can barely see it. And you're like, that's lame compared to all the pictures of Jupiter I've seen. Yeah, that's because they're taken with the Hubble Space Telescope and these giant observatory scopes, or by spaceships that are right next to it. So the pictures aren't as good as the ones in your book. But it's kind of addictive when you start looking at these. You look and you see it, and you're like, if I had a bigger scope, I could see it better. And so you want to buy a bigger scope, and see it a little better. Telescopes get kind of addictive They're kind of expensive. There's a logarithmic curve to the expense of a telescope. As you get bigger, you go whoop, you go up like that. I mean, it can get a lot more expensive. Let's take a look at these big scopes right
Telescopes. Sitting atop Mount Graham, a 10,700-foot mountain in southeastern Arizona, the LBT utilizes two giant 8.4-meter primary mirrors that allow astronomers to explore distant planets in our galaxy and obtain crucial knowledge about the origins of our universe. With the utilization of next-generation adaptive optics, the LBT will attain the resolution of a 22.8-meter or approximately 75-foot telescope. This allows the LBT to achieve its potential as the world's most powerful optical telescope. Developed in a collaboration between Italy's Arcetri Observatory of the Istituto Nazionale di Astrofisica and the University of Arizona's Stewart Observatory, the LBT's optical technology represents a remarkable step forward for astronomy.
This telescope is unique and first in having a full-time adaptive optics secondary mirror. What that means is that the light from the sky strikes this giant 25-foot primary mirror, which starts to bring it to a focus. Just after it goes through that focus, it will hit this adaptive secondary mirror. The secondary mirror reverses the path of the light and sends it back down toward the light analyzing instruments at the bottom of the telescope. However, that mirror is of a very special construction. The mirror is 36 inches in diameter and about the width of a few human hairs. It's 1.6 millimeters thick. It has 672 voice coil magnets glued onto the back, and we change the shape of the surface 1,000 times a second to compensate for the air boiling around above our heads. So that sharpens the image back nearly to the way that it would have been delivered with no disturbing atmosphere at all.
So that shows it real well how they got the
initial images taken with an
how they got the picture better. I think they show it here. So that's a picture before these adaptive optics techniques.
Infrared test camera developed by LBT's Italian partners
And that's a
demonstrate how the adaptive optics system corrects the blurring and motion artifacts created by our turbulent atmosphere. LBT's adaptive optics system first came online in 2010 and immediately outperformed all other comparable systems, delivering an image quality greater than 3 times sharper than the Hubble Space Telescope.
So you can see this. So this is what is seen without the adaptive optics. It's all blurry. And this is what it looks like with. You can see it's actually 3 things, 3 separate stars instead of one blurry object. That's a huge difference.
When the adaptive optics are in place for both mirrors and their light is combined, it's expected that the LBT will achieve image sharpness 10 times that of Hubble. Developed as an international project, LBT partners include an international consortium of scientists from the Arizona State University.
So there's all these different telescopes that use this adaptive optics system. And we use the word resolution. Resolution is a word that means better focus, less blurry. So we would call this a high resolution image. And this is the same image at low resolution. And you can't make out that moon at all. That's one of Jupiter's moons. That's Io, Jupiter's closest moon. And here you can't make that out at all. So what we want with these telescopes is a better resolution. Now, not all telescopes see visual images. Some, remember, we just studied all the different types of light. There's radio, there's infrared, there's visible, there's ultraviolet. We have telescopes for each one of those types of light. This is a radio telescope. It's the largest telescope in the world. It's the Arecibo scope in South America, and it's built in a depression in a mountain. And that disc right there is huge. You could fit several football fields inside of it. And it takes radio waves, and the radio waves bounce off of it and go up to this collector here and makes an image. It's a giant scope. They filmed a James Bond movie there. Did y'all ever see it? James Bond was running around shooting villains, and he ran up on this thing, and then he came down on a line, and it's really cool. There's also a movie I have back there that you can take home and watch. It's called Cosmos, where they're using this to try and communicate with alien civilizations. A lot of times they'll set up these radio telescopes. That's a giant radio telescope. And if you notice, they got them on train tracks. And they can move these scopes from place to place. They can put them on a track and move them somewhere else. And they string them out in long lines. And then they hook all the scopes together. This is called interferometry. Let me see if I have a better picture of this. No, I don't. But what they'll do is they'll hook these scopes up, and they have them like in a configuration like a big peace symbol. They'll have scope, 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 and then they'll have them going out like this, and then they'll have them going out like this. And every one of those scopes is pointed at the same thing. And it makes it so it's like one giant telescope, like this big.
So what does interferometry mean?
Interferometry is when you hook a bunch of telescopes up together and have them all looking at the same spot.
So it works as one big.
It works as one big scope. Each of these makes a separate picture and feeds it into a central computer that's located in a building right here. And it's almost like it's one huge scope, because this is getting information from here and this is getting information from out here, and it can take all that light and put it together for one picture. We call that interferometry. And there are several types of telescopes that use that technique. These things are giant. This is called the Very Large Array. It's in New Mexico. I have these YouTube links in your book. I want you to watch those. They talk about each one of these, and we're running out of time, so I can't talk about all of them. Another thing you want to do if you want to get out of the atmosphere and not worry about atmospheric interference, you launch your telescope into space. This is the Spitzer Space Telescope. And it's an infrared scope, mostly. It sees heat, not light, not visible light. It sees heat, infrared rays. But it's been flying out there in outer space, orbiting the sun, and taking pictures of space, and there's no atmosphere to worry about in space. And our atmosphere really blocks infrared. So if you want to see infrared, you got to get above the atmosphere to get a real good infrared picture. That's the Hubble Space Telescope. Who has that? Doesn't somebody have that as a project? Nobody picked Hubble? Anyway, the Hubble Space Telescope's been launched up there and it's taking pictures. It's got visible and ultraviolet and infrared capabilities.
Didn't you say the one on the ground though was better than that?
The one on the ground can see things more closely, but the Hubble can do things that can't be done on Earth because of the atmosphere. So they're different uses. But the Hubble's taken a lot of great pictures. That's a picture of a far-off galaxy from the Hubble. This is the Chandra X-ray telescope. That's also been launched into space. We've got a few of them up there in space. Chandra, Spitzer, Hubble. You hear about the Hubble, but there's actually several of these observatories floating around around the Earth in orbit. And that one sees X-rays, whereas Hubble sees visible.
Wait, it says visible and not ultraviolet?
Hubble?
Yeah.
Hubble sees visible, and I think it also has infrared and ultraviolet capability. Uh-oh. We're out of time. Why didn't it ring in here? Oh, the James Webb Space Telescope. That one's going to be launched soon, and that's going to take the place of Hubble. It's going to see something like 20 times better than Hubble can see.